Welcome everyone. Thank you for joining us for today's TASI webinar, Turkish Association for Seismic Isolation. My name is Mehmet Emre Özcanlı. I'm the president of TASI. In TASI webinar series, worldwide reputed seismic isolation experts present on seismic isolation applications in their countries. Today, we are presenting vibration control systems in a high seismic country, Chile, a design and maintenance perspective, by Professor Ruben Boroschek from University of Chile. If you have any questions during the presentation, please type them into the question box in our TASI YouTube channel chat panel. I'll bring them up during the presentation, and we will also have time for questions at the end. Especially, I would like to thank Mr. Paolo Clemente, who's Assisi President, as he distributed our webinar announcement to all Assisi members throughout the world. Dr. Ruben Boroschek, our presenter today, recently is a professor at University of Chile, teaching structural dynamics, advanced structural dynamics, seismic design, structural analysis courses in the university. He is also board member of Cosmos USA. In addition, he is CEO and main partner of RBA company located in Chile since 1999, dealing with seismic design, seismic review, and forensic study. He accomplished more than 300 projects during last 10 years. He is also recently corresponding member of Mexican Academy of Engineering. He has received his BSc degree from University of Costa Rica, both MSc and PhD degrees from University of California, Berkeley. He taught at University of Costa Rica, was research assistant and visiting scholar at University of California, Berkeley. He was also director of Strong Motion Network at University of Chile. He has authored several scientific publications, and specifically, his research area is focused on strong motion simulation, experimental dynamic, and structural health monitoring, vulnerability assessment of critical facilities, base isolation, and passive energy dissipation, damage assessment of structure, healthcare facilities, vulnerability studies, and mitigation. He was selected Engineer of the Year 2017 by Structural Engineering Association of Chile. He got Ramon Salas Edwards recognition for the best paper in 2014 by the Institute of Engineers Chile. He got honorary professor title from University of San Antonio Abad de Cusco, Peru in 2011. Now I would like to give the stage to Professor Ruben Boroschek.
Thank you, Mehmet, and thank you, Tasi, for the invitation. It's a pleasure to be able to share the experience that we have had in Chile and Peru on base isolation and energy dissipation devices. So I think your seminars by Tasi, it's very important, because it shows the development and the good and the difficulties that we have in the design, construct, and maintain this type of system that I think they are of great benefit to the community. Let me share just a second. Okay. So hope you can see my screen, my pen. Yes. So this presentation, I'm presented myself, but actually it's a joint presentation by my partner for the last 22 years, Rodrigo Retamales. And I'm gonna show the work that we have done at the University of Chile, that is the bed of this seismic isolation in Chile, but also what we have done in the private sector, designing and help design structures. But I don't want to focus only on the benefits of the seismic isolation and vibration control, but also I want to think in terms of maintenance and constructability, because after we have some buildings that are more than 15 years now, one of them is very old, actually prior to these 15 years, and we are facing now with the issues of maintenance, reliability, and modification of the structure. So I want to focus on that, but in the scope of Chile. Chile, it's located in the southern part of South America. It's a 4,000 kilometer long country, it's the average width is only 150 kilometers, but we are in the contact of the Nazca plate here and the South American plate. And these two plates are moving as is one of the fastest moving plates in the planet. Actually, from a very old paper in the 80s by Ruben and Kanamori, if you compare the rate of movement between two plates and the age of the plate, and you order the earthquake, so magnitude 7, 7, 5, 8, 8, 5, and 9, and you arrange large earthquake in this upper corner, you will find Chile, because of the very rapid motion of the plate. And this is our problem, because it means that we will have, and I'll show you, a lot of earthquake, a lot of small earthquake, but that can cause small damage, but also a lot of large earthquake. And we have to deal with that with the same passive control system. If you check the, for example, for 100 years, the last century, the earthquake energy in the whole planet, you take Chile contribution to the world seismic energy is 46.5% of the total, and all the other countries are 53%. So actually, we are in an odd condition due to this high-speed plate. And so we are dealing with that for many, many years. And we have developed specific design criteria to deal with this high seismicity. In Chile, we have a subducting plate, the Nazca plate, and a plate on top, continental plate, a South American plate. But due to that, we have interface earthquake, and these interface earthquake are pretty large. The larger we have had for the moment is 9.5, but we have an interface earthquake of magnitude 8 every 10 years, or 8.5 every 15 years. Also, we have what is called intermediate depth earthquake on the subducting plate. And these are very, not as common as this one, but they're actually, the larger earthquake here are magnitude 8, 8.2, and they occur as often as the interplate. But the problem is that we are actually on top of this earthquake, and so we have very high accelerations on the surface. And these are also very long earthquakes. And as you will see, this is one of the conditions that we have to design for is duration and high accelerations. Also, of course, due to the stress, we have surface cortical or shallow earthquake. And these are not so often locally, but we do have some, and we have to design for that also. So this is our environment. We have other type of earthquake that I'm not going to mention because it has not affected us lately, but we design at least for the three of them that I have showed you. So here I'll show you the big earthquake from the 1500s till recently. This is the year on the top, and on the bottom you see the country, like 3,000 kilometers here, and this is our political border with Peru. And these red lines are rupture areas of magnitude 8 earthquake. So you can see that, and this is the table that generates this figure. So if I only list the magnitude 8, and you just check the last 10 years, well, we have 3 magnitude 8s in those 10 years, and a lot of small earthquakes, okay? Small meaning magnitude 7, huh? That occur every 5 years. So this is not a small for the other part of the country, of the world, but for Chile, these are damaging earthquake, this magnitude 7, but only for weak structures, okay, and non-structural components. So they cause some economic loss, okay. But our major concern are these magnitude 8 earthquakes that occur every 10 years, somewhere in these 3,000 kilometers. It's not always in the same site. Actually, if you look at one side at a time, and you see the history, you get magnitude 8 every 90 years, okay? And many buildings, many structures, due to the size of a magnitude 8, actually receive earthquakes influence or accelerations that could be every 20 years. So actually in our lifetime, for example, in the central part of Chile, most of the buildings have received the seismic demand similar to the design demand more than once, maybe twice, and sometimes 3 times, okay? And we have to deal with that also. But the issue is not designing only for the big ones, because designing for the big one is appealing, but people are looking for economic protection of functionality of the infrastructure. So we have to worry also about the more recurrent earthquakes. So here is a seismicity of magnitude 6 and above, okay, for only 16 years, okay? So you can see how many magnitude 6 or larger we have every year here. And this magnitude 6, of course, doesn't tell you anything about accelerations, but I'll tell you they range from 1 to 6%, okay? So they are not easily felt, but some of them are pretty large. And you have to worry about this because typically we have 7 to 10 of these earthquake every year. So every month and a half, we have a magnitude 6, okay? So we don't want a system that is locked at these acceleration levels, but we cannot release the system for very low friction or yielding system because we have also wind. So there is a limit there that we have to discuss. I want to just show that we have this problem. We have a lot of earthquake with acceleration 1 to 3% in each side, maybe twice or 3 times a year in each of the country, 3%, and 5% maybe once every 2 years. And what happens if we have an elastic structure that is not isolated? Let's say it's base isolated, but it doesn't work for 5% or 8% acceleration at the base. So we will get in the upper structure a very high acceleration. If you think on linear theory, it will be 2 times or 2 or 3 times, 2.5 times the base acceleration. And those are pretty large accelerations. You will get functionality disruption and some local damage that will need repair. And if you have to repair every 2 or 3 years, then you are in trouble, okay? So we have to handle something that will start working as low as possible with a certain confidence, but also that it will work on the large earthquakes, okay? So that is the condition that we have in Chile. That is not so common in the rest of the world, as I know, but we have been living with this for many, many years, and we have some solutions to these problems. So one of the largest, the largest earthquake in the world occurred in 1960 in Chile, and there was only one isolated structure, was a test structure in the southern part of Chile, in a city called Valdivia, and suffered no damage. Okay, it's a sliding, roller sliding structure at the university. But in 2010, we have the 6th largest earthquake in the world, a magnitude 8.8, okay? And it covered an area that is nearly 500 kilometers by more than 180 kilometers wide on the rupture, and the affected area was much larger. Actually, the average acceleration in all this area was 0.3 G in more than 600 kilometers by 200 kilometers. But we didn't have too many deaths, but we did have of them. A third of this death is caused by tsunami inundation, and only 20 deaths were caused by civil or engineer structure. Most of the death is what is called adobe or mud housing. Okay, that was an unreinforced masonry. But we have a lot of loss, economic loss, and this is due to content and functionality problems. So this trigger in the 2010, I may be wrong, but maybe we did have like 5 or 10 maximum structure with base isolation in the whole country. After this earthquake, actually, we started designing, at least in our office, 1 or 2 buildings per month, okay? But during this, after this earthquake, we have like 13,100 aftershocks. So a lot of them with magnitude 6, and some of them with magnitude 7. So it was pretty difficult to handle this situation. And all the isolated bridges and hospitals, there were 2, behaved perfectly, no damage, just minor non-structural damage at the interface. So it showed that it's a very good solution. And after that, people got some confidence. And so that's why we are, at least in the Latino countries, one of the countries with the largest number of protective, that using protective systems. But I want to focus on this thing of the earthquake with large magnitudes. So here's a record from this magnitude 8.8 or 210. These are triaxial accelerometers. And you can see here that we have 2 horizontal and 1 vertical, okay? This is the up-down and 2 horizontal here. And there are many things you can see on this record. One of them is length. Duration is very long here in Chile. Actually, we are so used to 1 minute or 2 minutes vibration, 2 minutes here, that it's not odd that we wait at the beginning of the earthquake 5 to 10 seconds to see if it's strong or not. And then we do take action as a people inside the houses or everything. And then we have very high acceleration. Actually, here is around 0.3, but this is 0.4. We will see not only on the horizontal, but also on the vertical, you see some sustained vertical acceleration close to 0.4 G. So this is a key issue. Numbers of cycles is humongous here in Chile. And I'll show you some examples, okay? So we have a lot of cycles of strong motion, okay? And also high vertical components, even that is an interface earthquake and that we are, as I'll show you, far away from source. So I'm gonna take one of the components I just showed you, the horizontal, and we draw it here, is the blue trace. And here is the green line is 5% G. And you can see how many cycles we have with 5% G, maybe 1 minute, 90 seconds, 1 minute and a half, or a little bit less. How much time we have with 10% G? We have like 70 seconds, and 20% G in this condition, not so much, 20, 25 seconds. That's a lot, but compared with the rest of the earthquake, well, it was okay. It was impossible. I was close to the area during the earthquake, and it was impossible to walk or stand during the 1 or 2 minutes, okay? 1 minute was difficult to stand, and the rest was, you were shaking because of this. You were scared, but also because the ground was shaking. But also on the vertical direction, if I do the same, I take the vertical direction, and I check, for example, 20% G line, and you have, again, like nearly 25 seconds of very large vertical component, much higher frequency, of course, but this is important for sensitive system, okay? Sensitive to vertical systems. So this is one of the conditions. Of course, the demands are humongous, but I did something on this record. I took the horizontal record. This is actually, it's a soil type D. It's a sandy with some line in between. layers on a valley that is 120 meters deep. So I took the acceleration record, but I filtered the signals to only see 1 second bandwidth, between 1.5 seconds to 2.5 seconds, in order to count the number of cycles on on long period signals. And you can see here that it's concentrated here. Very large cycles are around 5 or 6, but nonetheless, we have plenty of smaller cycles that are pretty large. And here I integrated the data, the same bandwidth, and you see here that the displacements are important, also 10 centimeters, but this is at ground level. This is not response spectra. This is the actual ground motion. And if you check the buildings on the area, you see this, and this is just a picture of a very common failure. This is a 10 or 15-story building, and this is after the earthquake. Nobody cleaned this joint. This is more than 40 centimeters, and there is no concrete. Actually, all the concrete is in the ground because the number of cycles is so large that just the concrete fell out of the location. So this is actually how it ended up after the earthquake. No cleaning was done on this wall. And I can show you plenty of examples due to this cycling. So large earthquake, magnitude 8 or 7.8, as I'm gonna show you, and duration is a key issue on designing. So if you have a system that is sensitive to cycling or large number of cycles, then you have to be very careful on your design in order to not to run into problems, or that it's stable. I mean, some of our systems, base isolation and energy dissipation devices, heat up a lot, and the properties change due to temperature, and we have to consider that, okay? So it is possible, but you have to be careful. Of course, the response spectra of that record I show you, the blue one is this one. These are the horizontal ones. You can see here very long period motions and very high amplitude for 5% damping, okay? Damping here, sorry. So we have very large accelerations, and in the displacement spectra, 5%, we have very large displacement at 5%, of course, okay? And in both directions, and in the vertical direction, actually it dominates the response on the lower frequency of the system, but it's not so small, even for 2 seconds, okay? So this is something that we have to worry about. We have many sites with, this is caused by the valley effect on the area of Concepcion. This is the record from Concepcion. But we have, at least in the capital city and many other areas, sites with 3, 4, and 5 seconds period, natural period of the valley. So we have to consider that also in our design of the base isolation conditions. Okay, and this is a pretty broad peak for a response spectra, and this is caused by nonlinearity of the soil. So actually you can see that the initial peak is around here, and then it moves to longer periods based on the nonlinearity of the soil that you should also consider. So if we design here, we will try to put our isolated structure around here. Actually, in the city of Concepcion, all the buildings that were located in this period at the initial of the earthquake went up the steep demand, increased the demand with damage, and 25% of all the buildings, tall buildings in this city has to be demolished, not repaired, demolished, 25% due to this condition. But we only have one failure, okay, one collapse. And that is, okay, not for the people on the building. But I don't want to give you the impression that we have this type of record only on this large 8.8 earthquake. I'll give you another example, and not so large for us, 7.8 earthquake, an intraplate this time, that occurred in 2005. But and here you can see, so this is the horizontal and this is the vertical. Okay, vertical, horizontal. So what you see here, again, the same situation. This is not one of the largest earthquakes that we have had, but duration, again, is not so bad. I mean, it's only 50 seconds or a little bit less. But the strong motion duration, depending on what you measure, but very large acceleration, 25% G on the horizontal for nearly 25 seconds. But look at the vertical. The vertical that has a 0.8 G acceleration, or let me forgot to tell you, we are 120 kilometers away from the source and still get 0.8 Gs on the vertical, but that's not a sustained acceleration. Actually, the sustained acceleration is 0.4, but for 25 seconds, okay? So again, you have to be worried about how you design for this huge number of cycles and large duration. Okay, so in 2010, we have 8 million, around 10,000 buildings on the tall buildings, not tall buildings, but mid-sized building and tall buildings in the area. And of those, only 5 collapsed in the whole area. That is less than 0.05% of the stock. And 50 at the end of the earthquake. And after reviewing, we have to demolish only 0.5%. So this is very good. It means that we did have damage. We didn't lose too much people, but we did. And there was some collapses as this one here. And why we didn't have too much collapses in a standard building? Because since 1906, we have been designing in Chile with a lot of shear walls in order to restrict collapse, but also to resist the frequent earthquake. Because we have a magnitude 7 every 5 years, we cannot, and we have legal responsibility for 10 years, we cannot be repairing our buildings every 5 years. So what we have done since 1906 is to put as many walls as we can on a building and then restrict damage. And it has worked. So we did have some failures, of course, because of the duration. We have a problem with reinforcement, good reinforcement, similar cracking on walls. Due to the large number of cycles, we lost material. We have too slender walls. We have wall instability, etc. But the worst was not that. It was non-structural damage. This is the international airport after the earthquake. We have a lot of damage. And all our hospitals in the areas, earthquake areas, have a lot of damage on the non-structural component, architectural or industrial or lighting or other facilities. So after this, that we lost many hospitals operation and we have to demolish some of them, there was a strong sense that we need to change the condition from life safety, that is the red standard condition in Chile, to a condition where we protect the components, the architectural and all the non-structural components and the operation of the system. So that was our sad story of 2010. But then, because some of the isolated structures did okay, then we start designing some structure with additional. We didn't eliminate the seismic safety of the structure, but we added some additional system, some energy dissipation devices and isolation, okay? And we have used all the time high damping rubber, lead rubber bearings, and friction penetrators. So we have experience with most of the system. We don't have many of each of, but we do have some stuff there. So the first things we did in order to promote this, in 2003, before the earthquake, actually, we developed our first base isolation code. And then we updated after the 2010 earthquake, our national code based on the American standard, but with factors, I'm not gonna go into this, but we factor adapted to the typical earthquake demands, long duration, not so high velocities. The largest velocity is 70 centimeters per second. That is pretty high, but it's not so common. Actually, our records show high frequency components, and in general, so 40 to 50 centimeters per second velocities at ground level are pretty common. So what we do is we modify all the reduction factors by damping. We have some recommendation on inter-story drift for the superstructure. And one of the things that is important is that in Chile, if we use base isolation, particularly rubber bearing, we require that the vertical natural frequency be higher than 10%. And many times this controls the design of the isolators, okay? And other conditions that we can discuss if you're interested in that. The first time we did a formal design in Chile of a base isolated structure was a very small example to promote the technology in 1992. This was done by two leaders here in Chile, Mauricio Sarracin and Maria Ofelia Moroni. They lead this test with the advice and a lot of help from Professor James Kelly from Berkeley. And at the end of many years of testing and development, the government accepted to do a test bed with a regular building, nominal foundation, an isolated building just in front of it, okay? And everything paid by the government. And it was a very small structure, 10 meters by 6 meters on 8 isolators. And it has been in operation since 1992, and it has done very well in all our earthquakes. And one of them is this 2010 earthquake. I'm just gonna show you seismic records on the ground level. So you see here is done, this is 0.3 G, at the max PGA. This is the isolated top story of the isolated structure. It has a 0.22 G on the top, and the change of frequency completely. This is only longitudinal direction. And the other record, the building, typical building, had an acceleration of 1 G. Actually, the recorder saturated, so it has to be larger than 1 G. And it was damaged and cracking on these walls of the non-isolated structure and no damage on the other one. On the vertical component, we saw what is expected, that this is the ground level and the upper part of the two structures with isolation, without isolation, actually were not too different. The frequency content was different, and there was a little bit of benefit on the isolated structure here. So vertical is an issue, and we all know that, okay? So this is one of the examples, good examples that we have instrumented. We have some bridges that are instrumental. I'm not gonna show that, but we have some info on that. Before 2010, we already have some big structures isolated. A large hospital that is a single plate that is 300 by 300 meters that we were involved on the design of this hospital in some of the components with an isolated component here and an unisolated building here. And during 2010, this earthquake, this building suffered some damage, and this component, nothing, just small joint problems at the isolation level. And we have some metals, elevated highways with some degree of flexibility that was considered in the design, and some pretty large single beam. This is a 380 meter long single beam, no joint, on top of isolators here that you can see. So this is, we place the isolators first, then we launch the beam, and when the temperature was 21 degrees, the whole beam was lower, so we don't have too much stress due to temperature deformation on the isolators. All of these buildings went through 2010 without any problems here. Accelerations were close to 0.5 Gs, and in this area, it was 0.3 to 0.4 Gs. So actually pretty large accelerations and long durations, no problem. After that, we start designing a lot of buildings with base isolation. And amazingly, one of the key issues was to isolate residential buildings. Why? Because people were scared. There were a lot of structure aftershocks, so people didn't want to buy regular standard buildings. So we went into designing residential buildings, and this was one of the tallest for many years. It's 16 stories, if I'm not wrong. And we designed it with a colleague, Patricio Bonelli. It's an excellent designer. And we designed the base. And the idea is to, and you can see the shape, we put isolators on the bottom, and we use lead rubber bearings, and has gone through several earthquakes already. And we instrumented this building because we tried. Every time we do a isolated structure, because problem with the seismic gap, people always try to modify the gap or restrict it. So in critical infrastructure, we instrument the area and try to determine in continuous time in an autonomous system the stiffness of the isolated layer. If we detect a stiffening that is not reasonable, then we send a group to inspect. So in this building, we have measured a lot of earthquakes. This is the displacement spectra of one of the recorders. Inside, actually, in one of the big earthquakes, I think it was magnitude 6 or 7, the people jumped on top of the building that were outside because it was moving more comfortably than outside because it has no high frequency. So they felt that it was safer and no damage in this structure. This video is from the same company that provided isolators, but it's not the test of this building. It's a different test. So one of the things that we are trying to do always is to have something to validate during construction and during operation that the seismic gap is maintained and the isolation has maintained its properties. So now in all the hospitals that are complex or large size, we are requiring to have an instrumentation in all of Chilean hospitals that will report if there is something happening on the isolation layer. And this is a view of that building. You see 2-meter deep beams, some pretty thick, and isolators quite clean, has been like that for, I think, 7 or 8 years already. Then with another group, we went higher, actually, to 33 floors, isolated structure. So we isolated these 2 buildings with a common platform. And this was a very, it was quite challenging because the original period of the structure was pretty large already, 2.7, but the owner wanted to have isolation in order to be able to sell it faster. So we designed an isolation that increased the period to 5.5, maybe 6. Actually, it's 5.5, what we have measured during some testing we have done. And of course, in this very tall building with a common foundation, we have a very thick mat here in order to lower the center of gravity of the whole thing because it's very narrow, as you can see. But the benefit is not perfect. You can see the prior to isolation on my left, and isolated, you see there's still some deformation on the upper structure, but conditions are quite good. And it has been accepted by the users. This is a residential building, and we are in year 6 of operation of the building and without complaints about the isolation. One of the tricky things here is that the site is very small and the isolators are humongous. This is in Pavia during testing. So you can see here, it's a nearly 1.6 meter diameter. And at least in Chile, we require all the isolators to be tested. Not only prototypes, all the ones that go to site in order to validate at design level that we have the proper conditions. So these were tested, okay? And the problem of handling this in such a confined space, it was the weight of these things, humongous, that we need a special crane. But also, it was one of the things I want to mention, these huge isolators have problems in the construction due to the pouring of the grout. So at the beginning, the people were using a standard grout, even that we recommended other. And they have a lot of failure with a lot of voids on underneath the plate. And that is causing a lot of problems, as I'm going to show you. And in this case, we, as designers, we require, at least at the beginning, to remove the isolator once this was poured to check that they already have a good grouting system. Actually, after several failures, we required the contractor to do this in a lab with a crystal plate of the same size until they were able to pour the grout and remove all the voids. Then we allow them to go back and do it. And then we check and they actually learn it, and then they put all the isolators without any problem. And for the moment, we have no problem. Actually, these isolators were so large because we needed to have the 10 hertz or higher frequency on the vertical direction. So the vertical component controlled the design. Also, we were quite worried because 10 hertz is quite close to the natural frequency of the slabs on the vertical direction, and we are close to a pretty busy street. So we don't want trucks and buses inducing vibrations in the vertical direction. We are not isolating. And also we don't have too much damping on the vertical due to the isolation and the building itself. So we have very low damping and maybe possible resonance. So we have to be very careful in the design to control this annoyance. That we were able to do it, was no complaint at the end. We have done many of these. I'm not going to show you or bother you with that, but some very large ones like this one, again with Bonelli. It's an L-shaped structure, very heavy, typical dampings. We tried not to go too high, 20%, and periods are around 3 to 4 seconds unless it's something special. One of the nice projects that we did sorry, just dropped my headphones. This condominium. Actually, it's we isolated the whole block, nearly 150 by 150 meters. And it was designed with 3 buildings and an apartment, and everything was designed. Actually, the isolators were built and sent to Chile, and then there was economic problem, and the project didn't went through. But everything was already bought, the land, the isolators were in Chile, so it was terrible. But this is one of the nice projects that didn't went through. Actually, the isolators were resold to other companies, and they were used in different projects, and they have to adapt the project to the isolation properties that were designed for these three tall buildings on the same platform. I hope we can do it, but not in the near future because of the COVID. So we have done many buildings, office building, more than residential now, and a lot of hospital projects we have been involved, and some of them are under construction now. Typical buildings are using 10 to 30 isolators, but hospitals, the largest one we have designed is 600 isolators. So it's pretty large projects. And the other area that we have been working on is data centers. So here we are using rubber isolators. This is one of the cases. This is one of the largest data centers in Chile or even I think in South America. We're just finishing an addition with 100 something isolators in addition. And this is in a not so good soil, high seismic zone. And again, we try to use lead rubber bearings. And one of the nice things about these data centers that they ask us to design in order not to, for the design earthquake, not to overpass an acceleration. So it has to be a limit on acceleration. And in order to, we did the design for that, and in order to beat the security level that it was required. But in order to validate that, they require an accelerometer network that will, in automatic sense, will detect the earthquake at the ground level and the upper structure, get the drift, get the appropriate stiffness. But the most important thing is that the acceleration did not, it was not higher than the design acceleration that was pretty low, but I'm not so sure compared to the next one I'm going to show you that was very low, but this was around 0.10 or 0.15 maximum. Don't remember the number now, but it is designed for a maximum acceleration and controlled by an accelerometer system. In another project that is for a telescope, we designed the isolation for the data center again, but here the limit was pretty low. So we decided to go by cross-linear bearings. Okay, so it's a mix that we have done. You can see the cross-linear bearings. Those are very low. Friction coefficient is around 0.8%. Okay, and in order to have recentering capacity, we have some rubber bearings, lead rubber bearings to get some damping also a little bit. On some of key positions. So in order to get these requirements of very low acceleration, because these are data centers with tier 4 level, that means like they cannot be out of work for more than, I think it's 8 minutes a year under any event, even the maximum earthquake. So under that condition, we need to be sure that we have very low acceleration so the computer system that is inside can sustain that acceleration, and we need to guarantee it. And it's more expensive, but it's easier to guarantee because it's quite linear, okay? And other type of friction system and even rubber system, we cannot control so much the properties as you may know. But other examples is we have used viscous systems as a diagonal on new projects, not as a repair project. And these systems are not so common. Maybe there are like 5 or 6 in the whole country. They have not been used because they still prefer walls. The architects still use walls at the elevator and at the stairs. So that restricts a lot. We don't use mummy frames a lot in Chile. So relative motions between floor is very small. So you need to amplify the motions of the dampers. And at the end, it's the architects don't like it so much. So we haven't used it too much. But in the industrial sector, on the contrary, we use it a lot. Actually, we were involved in the 1993, very early, putting some, or reviewing actually, some friction dampers for large transformers. So you can see them here. These are, in this case, ring feather stuff, ring friction dampers, and with a triangular hysteresis. And we helped to install those in 3 substations that were in the epicentral area of the 2010. And it's amazing because you see this picture is after 2010, and there is another one I cannot show you, but all of the other ones without isolators, dissipators are on the ground, broken. So this shows us that this rocking system, this rocking dissipating system is very effective. So, and this one and the wire rope is quite used in Chile in all electrical substations. Also, we have done some our own development. For example, we have a bridge that have gone through this two times design earthquakes on is 36 meters from the ground, and we designed it. This is a pendulum between two. This is a 22-story building. Here is an 11-story building, and these two buildings move independently, of course, and the bridge has to follow. So we designed some rubber tendons, pure rubber, with some chemicals, in order to control vibration to human-induced vibration by walking on the bridge. So, and then also when compression comes, it works as a bumper. So actually, the hysteresis is something like that. We developed the shape and the conditions, has been in operation for, I think, 17 years now, yeah, from 2003. And we usually inspect it every 5 years, and it have gone through two situations where the buildings were subject 0.3G at the base. So the motion were huge, and no single crystal on this crystal bridge broke. And I hope the cause is our vibration control system. Also, we have used in Chile and in Peru, in our office in Peru, actually more in Peru than in Chile, some buckling restraint braces. And these are, we provided in the industrial sector to control damage and not to repair this structure after each earthquake. So we don't want to go and do repairs. So some of the new structures are replacing their standard diagonals that have to be replaced after a typical earthquake with this unbonded brace system, in this case from nipple steel. And we have done some TMDs. We designed 8 buildings, 2 of them already built, large masses that control the vibration of the structure. We didn't reduce anything of the seismic safety. It's just for comfort. I don't like this system too much, but people want them because it allows them to sell more quickly the structure. We do it with a lot of safety factors, but efficiency is not so large. So it's not what I recommend, but we have done it. Bridges, of course, we have done some of this. I'm gonna go faster. And I want to go to some of the problems we have faced or we have seen that other people have faced, and because not everything is done on the board. A lot of things are done on the ground. And I think if we don't think on the ground on the long term, we're gonna get into trouble. First, there are some designs that are pretty hard, like the ones I'm showing here. This is an isolator with all the boards here, but the distance between the board and the rubber cover is so small that the contractor didn't bother and just took out the rubber in order to put the board. And this is a design problem that we should avoid. And I think it's restricted by the lower pedestal, but this is something that we have to think, constructability. I mean, the distance, the number of boards, and I'll show you several examples of this sort so you can have a sense of what we have experienced. Just a second. Okay, so other issue, for example, an energy dissipator that was placed in the main airport in Chile. So we have here the dissipator, but the designer thought only on tension forces and put a gusset plate that is a machine plate. And you can see here that is completely bent. So this is a mistake of the forces that are generated here are humongous. Actually, I cannot show you that there are some dampers that are 1.5, 1 meter diameter that just ripped all the bolts of on the support, all the gases, everything, because the forces are humongous. And people are thinking on the forces on the dissipators, but they have to carry it to the supporting structure. And this is one example that was not done. Actually, they repaired this and they didn't replace the plate, the gasket. They leave the same gasket plate, so we will see a similar damage soon. This is a project that is not in Chile, it's not our project, but here the architect did not allow larger columns, and the isolators needed to be large due to some displacement. And so the architect allowed us to do some like a pedestal, and this is pretty bad because this is for a parking lot area, and you can imagine the overturning, the eccentricity problems, and this is not the best conditions that you have to handle, and you have to discuss a lot with the architect because if we have too many restrictions, you get into trouble with this architectural condition, as I'm going to show you in some other examples. Other problems we have seen, and it's quite often, is overloading. I mean, very large depth loads that give you negative stiffness on the hysteresis, okay? And here in this case, it's just too much. Even you can see the extremely high conditions, just a problem. And this can occur, of course, in rubber or friction pendulum. It can be even worse because you have the area of the compression could be much smaller. So this is an issue that has to be addressed and restrained. Our code and most of the codes will not allow such high compressions, but we still see them. The other things that you have suffered in Turkey is the issue of demands. One has the best will to estimate the maximum displacement, but sometimes new sources appear or earthquakes that are not considered have larger demands. So one of the issues is, what is the extra capacity of your system? If it's a fixed capacity, then you will get into damage or impounding or other types. For example, some rubber isolators are designed for 200 deformation, 200% deformation, but actually it can withstand without any damage 400. Okay, so actually, if you have the gap, you can go beyond that. So one of the issues is you're going to restrict yourself to your design displacement, and your system has no extra capacity, you may get some trouble because these are probabilities or not necessarily the maximum that will actually occur. If it's a critical system, maybe you will think on having some extra factor of safety on the system in order to accommodate extra design. And we have seen this in many, many projects that the capacity of the isolator is overcome, there is damage, and also we have seen that demands are much larger. The other thing, and I just want to stress an excellent paper by Calvi and Calvi. I really recommend that you read it. It's 2018, you haven't read it, about friction pendulums and all the benefits that you can get from friction pendulum, but all the care you have to do, because this issue, particularly in our country, that we have a lot of earthquakes that are not the design earthquake, the breakaway friction and the stick-slip behavior, it's important, okay? We need to consider that in our design. And we need to consider the reliability of the materials that are used for the conditions that we have, okay? And you know that some of these isolators have been replaced, others have to be redesigned or fixed, as I'm gonna show you an example. So one of the issues, still recommend this article, please read it, you haven't, is we need, if we wanna work on low amplitude but damaging earthquake and large amplitude, you need to be sure that your breakaway friction is not 8%, 10%, or 15%, like some of the isolators, friction isolators have seen, or with some rubber isolator with large diameter rubber lead plugs will cause a lot of problems. At the beginning of our design practice, we use a lot of lead in our designs, and we have a lot of problems in small earthquakes. So we decided to reduce the diameter to the minimum, so long we can accommodate the displacement, in order to have a good performance or during a small earthquake. So we don't have so many complaints from the clients that they were supposed to be in an isolated building that they will not feel the earthquake, and they feel all the earthquake that is small, and they haven't seen the big one yet. So this is something that has to be considered. This is another architectural problem that we typically have. They put only allow the isolator joint in the parking lot, so we have always cars in between. I hope that these cars will just be moved by the earthquake. Who knows what's going to happen? Also, it's fabrication problems. We do have to test isolators. In Chile, we decided to test all of them. And we have a lot of surprises, because when you have a percentage of testing, you will always get some weird responses on non-tested isolators. You don't just do the exercise. So in the testing, you see all the initial problems, misalignment of plates, problem with rubber, compound, and many others. You need to test. And at least in Chile, we are not taking chances, okay? The other issue on fabrication is, for example, for viscous dampers here, I don't know if you can see, but here you have some drops. And this is just a couple of months after this viscous damper was installed in an office building. And this jar here is collecting all the liquid from the damper. And actually, the whole building had these jars. All the dampers provided by this company, I'm not going to mention, leak on less than 2 months. And now the building has these dampers, and the company was a very small company and did not have the money to replace the dampers. So I don't know what happened there. But now we have this problem. So this is a seal problem, and it's a fabrication problem, should have been tested before. And this is a problem with these companies that are just a name, and they buy from third parties and put their name on top of it, and then they cannot replace anything because they are just a name. And we have similar issues with design problems. This is an actual bridge in Chile, and you see it's not supported on the concrete piers, but on steel piers. And why is this? Because the design of the isolators was not possible to be done at the factory. If you design what the designer did and test it, it always breaks. And after many, many tries, and not only the same manufacturer, others manufacturers, they have to change the design. But while they were doing this, they have to support the bridge on temporary scaffolding. And after that, another company was able to reproduce the requirements. They install it and then remove the temporary scaffolding. But sometimes you cannot do it. And this is a port in the northern part of Chile. You can see the cranes here, and you can see the cranes here. And this is an isolator that should go here, but they are still on top of the deck, because if you put it, they are so stiff that they will damage the structure below. This is, and they haven't solved it, and it has been more than a year with these steel columns that will be there for very long. And I think they will just leave it and wait for the earthquake, and we will see what happened with the cranes, because everything was designed assuming that the isolators will go here. But the designer, that is not us locally, just have some problems, okay, and cannot be solved. The same, the bridge, prior bridge is not ours. We will call just to see the problem and try to help. And this is the most common problem we find. Again, we are the reviewers of this project. Somebody on the construction forgot to put the grout. Believe it or not, there's no grout. So this is a 8-story building, so they keep building, and at the end, they just, this actually deflected and touched the thing here, and they call us to see how we can repair this. And this is very common. Grout problem is the most common problem. Actually, there is a lot of problem at construction because they leave, not this case that is extreme case, they forgot to put the grout, but to leave a huge voids under the plate, especially for large isolators. So you would really have to be very careful on how to place a grout in order to avoid high stress concentration. This is not the case for the, for the isolators. Rubber isolator is not so bad, but for friction pendulum, then you get into larger problems due to stress concentration. Okay, and we have seen that also. So trying to avoid as much as the void, you cannot have zero, but as much as you can is very, very important. The other typical problem, no, it's not the one I want to show you, but this is another design and construction problem. You see this bending of this beam because the height of the beam is too small. They didn't cure them properly. And then you have an isolator that is completely rotated and stressed due to this high deformation. So we were called for this. And at the end, this building has to be lifted and the isolator has no damage. And so everything were okay, but it has to be repaired. Also, it happened with sliders like this one, huge rotation here due to problems with the temporary structure. They remove it too early, and then you have high compression here and tension, uplift here. So actually, you have a high concentration on the lentil here, and then some damage on the area. So you have to be very careful on the construction because of that. Another common problem is that they have the inserts and they are rotated. So now they don't fit. And we have seen many things. Most of the things, when we see that the ball is not entering, we ask to remove the isolator and remove the concrete with some water jet and replace the socket rather than to make a larger hole in the plate. But sometimes they want to trick us. This is actually our project. And the ball didn't fit in, so they cut it and they just enter a little bit. And you can remove it just by with a small tool, uplift, just so the design doesn't see it. We have another case that they were a little bit smarter, so they put a epoxy in this area, but still we asked them to remove the bolt, and it was epoxy, the whole thing, it was fake. So the problem of misalignment is a critical one. It has to be very careful, has to be tested, tried, and a lot of supervision. So at least in Latino countries, you don't get into this very common problem. Other issue is that you design your building. This is not our design. This is an existing building, and on top you add a new floor, you put isolation, and then you realize that the other guys have a ramp here, and your gap is so small, but it's not your building. Okay, so you have a problem here, you define a gap thinking here, and not thinking on the reality and of two close buildings. So designs and construction is should be careful. I'm nearly finished, so don't worry. This is our building, but I'm not going to show it. It's a 20-something building. Here used to be, this is a seismic gap, and this was supposed, and it was a cover, but the seller of the building, the apartment, said that this cover was too ugly. We even designed the fence here to accommodate displacement. So he took out the cover and filled it with rocks, and he put some trees actually. And it took us nearly a year with letters going back and forth to be able to remove the stones. So actually we realized that everything that can be removed will be removed, and we need to do this with more fixed components that cannot be so easily removed because they will change it after 2 years, 5 years. They forget that it's an isolated building and they don't take care of it. So I'm not so fan of isolating residential buildings with a lot of owners and nobody taking care of it, but I prefer to do hospitals, office buildings, and industrial. Other things I want to pay your attention that we have a lot of trouble because we have an intensity 6 in a site every once a year. We need to, according to the code, we need to inspect. But if you have fire protection, then you have to remove it every year. And it's not so simple, especially if you are high on the ground. So inspection has to be possible. And fire protection is an issue that for us is complicated. So we have a mandatory 5-year inspection or intensity 6 inspection. And that intensity 6 in our case is so often that this is not so comfortable that we need the fire protection. So it's an issue that you have to consider. Also, some isolators, this is with water, as you can see here, have a protection cover that maybe it's not so tight in this case, and you cannot inspect it because the protection cover does not allow you to inspect. So if you have to inspect every earthquake or by some flooding, then how you do it without breaking the seals? Yeah, and those has to be thought because it starts to become a problem. Okay, maintenance. This is one of my first design with yielding devices. I think it was 1995 or something like that. So this is a 45-story structure. It's an industrial boiler. So it's hanging this boiler from the top here, 45 meters. So this is hanging and it's moving vertically because of the weight and the temperature. So here, the standard design in Chile was to get the exterior structure with some beam here, and the boiler has some 2 stoppers. And you design this beam that is here to yield here have yielding. Okay, so that was pretty cheap. I did it for 3 of these things in the 1990s. And then, of course, the earthquake came, 2007, and the thing worked. It yielded. You can see the gap here, and this is the stopper, and the damage was controlled, but they asked me to replace it, and we committed a mistake here because we welded this thing, and replacing the thing was impossible, so we left it like that because there was no possibility of replacing because there were so many elements, and it was no damage, so we said, okay, we will have another earthquake in 10 years. If this thing really goes bad, then we will do the work to cut here and replace the structure. So we always have to think on how to wanna replace this system. And one thing from Mexico I learned in 1987 after the 85 earthquake is that they put a lot of ADAS devices, steel yielding systems, and this is how you design it, okay? So you can see the diagonals, and you see the ADAS, you can easily replace it and everything. But when you see it on the site, the ADAS is under this ceiling and there is no inspection. So you have an earthquake, actually you cannot maintain anything unless you make a huge hole here, okay? And I can show you, maybe I cannot, but some of these have a fractured weld and you couldn't see it unless you remove the ceiling. So this is something that you have to also consider. You need to see the element in order to be assured the clients that you are doing the right job and everything went okay. And I think with that, I finished. Sorry for taking so long. I hope it has been an interest, and if there is any question, I'll be happy to answer them.
Thank you for a very interesting and excellent presentation, Professor Ruben Boroschek. We will go ahead and take some time for questions now. Just a reminder, please be sure to type your questions into the question box in your control panel in TASI YouTube channel. It looks like we have few questions I would like to read. From the beginning. I would like to start from Chile. Juan EPS, I think, from Chile. Greetings from Chile. A question for Professor Boroschek. Some codes specify vertical strong motion records with at least 2/3 of the horizontal acceleration, but say nothing about the frequency shift. Can you give us recommendations to consider vertical acceleration for synthetic strong motion records concerning the frequency shift? Example, the conception accelerogram you showed. Gracias.
Yes, this is an issue that has been changing on the codes. Many codes and our standard design did not consider any vertical, actually. Maybe a gravitational increase in some cases, but as you see here, this is the 2005 Northern Chile earthquake. I'm not going to worry about frequency shift, but I'm going to worry just to consider it. I mean, at least consider it. If you're going to worry about frequency shift, that's difficult, but I will recommend to use non-synthetic earthquake. I'll use scale records. If you cannot use a scale record, use an adjusted record with wavelets, very tiny adjustment, but completely avoid fully synthetic records with developed from random numbers generator, because at least the real records have the frequency shift on the demand incorporated. So I will first go for scale records, then from the same seismic zone, duration, especially, and soil conditions. If you cannot, because we can always do it, then adjust some record with tiny changes. Please don't do huge changes, and never go to a synthetic, fully synthetic. It's better to use a non-compliant record than a synthetic record in my case.
And also, I would like to tell Alessandro Martelli message to you. Happy New Year to you and everything. And also, Alessandro Martelli, Ruben knows me very well, similar to other Chilean friends, Moroni, yes. Saragoni, Sarazin, who are excellent experts at anti-seismic devices. And also, Oğuzhan Alperen has three questions. First one, firstly, many thanks for this great presentation. You mentioned that you are testing all of the isolators. The tests are done under the design loads then? Question mark.
Yeah, for production, prototypes are larger tested, but production, yes, for design load. Quality. Yeah.
Okay, second question. Oğuzhan Alperen, if ultimate loads are being used, how much safety factor is expected to say the isolator is okay?
No, we don't. For the prototype only, we use the maximum earthquake
yes,
test.
Sure. Yeah. And then third question, are relative big vertical loads comes from earthquake considered as additional gravity load by testing?
It is considered. Not always. We have not always considered the vertical loads in our codes. Okay, but recently, yes, we try to use the three components of our records. But this is more recent that we realized that we are starting to have this problem. Most of our designs are rubber-based isolation, so they are less sensitive to variation of the axial load, but we were worried on the amplification on the upper structure, on the vertical direction. And that's why we included in some of our tall buildings design the vertical component for comfort and also for verification.
Thank you very much. Also, Bahadır Şadan has 3 questions. First one, vertical component of ground motions are very higher than what we are used to here in Turkey. How do you cope with the uplift and tension actions on the isolators?
First of all, we not always have the vertical component on our design. At the beginning, we didn't consider. Okay, so we are learning from what we have.
Okay.
But now we avoid vertical uplift. I mean, we try any tension on rubber or uplift. We try to avoid it, and we always verify with records. In order to be sure that we are not getting into trouble. But this is a new condition, and as you may know, I mean, even that this record is 15 years old, I haven't seen it on a design of an isolated building or the other one that I show. I have plenty. It's not. I didn't have time to show you that this is a common stuff, and we do have similar amplitudes of demands depending of vertical demands depending on the period. So if you do a ratio of vertical to horizontal, you will get 2/3 at the PGA. Sometimes you get 1 at the intermediate period, and the longer period you usually get much lower than half. So it's the ratio of vertical to horizontal is period dependent in our case.
Okay. Second question from Bahadır Şadan. Duration of earthquakes are very long. How do you take into consideration the heating effects on both sliding and rubber isolators?
First of all, here we apply the code 10 cycles of design displacement. But here is a discussion, and I think the paper by Calvi and Calvi is the key that I want to rescue. I think it's very important, a key paper in our profession. I don't know where I left it, but I think temperature, especially for friction system, it's very, very important, okay? We didn't have, at least in the rubber systems, we used to have these 10 cycles of design displacement at 2 seconds. So it's pretty important, but we didn't have too much change, and I have plenty of those. But according to Calvi, if I didn't mistake the reading, he's the one that should talk about it. This issue has been brought even in Turkey, as an example, and they are trying to reduce the number of cycles for testing because friction try to they yield or melt at a lower temperature and easily reachable if you have a lot of cycles at high speed. So some groups are trying and don't like it too much to do sequential testing very slow. So you do a few cycles, wait, very slow, and then go back again. So you're not actually considering the real earthquake that has, in our case, it's not everywhere. I understand that it's not Europe's case, that you have 2 or 3 cycles, but here we need it. So not considering temperature effect is a mistake. So what is our solution? My solution and Rodrigo's solution is that try to avoid friction system. Use rubber with very little lead if possible, and have enough gap because we do have the problem.
Also, I can ask one question. Can you use multiple lead cores, or what's your perfection?
We only have used single lead core per isolated. We haven't done multiple lead cores.
Okay. Also, third question from Bahadır Şadan. Although most of the earthquakes are near fault, you said that the damping reduction factor used in Şili code is 1.94 for 20%, and 1.37 for 10%. These values are higher than the ASCII
Yes.
and in Eurocode,
Yes.
half of Eurocode.
This is because it's not impulsive. It's more, it's very long, constant, and it's not constant, but constant amplitude. We don't have a single shot, so we have a lot of cycles. Actually, if we will have to use that for cortical, if a superficial crustal earthquake controls, I wouldn't use our code. I will use lower, because then we have a single peak or less. Let's not single, but few peaks. Single peak is not going to help either. But it's because of what you see here. It's a lot of cycles.
And also, Eren Uçkan, thank you for this interesting presentation. Question 1. Are there any isolated tanks in Chile? If so, how was their performance during earthquake? If I am wrong, some wine tanks were damaged in Chile.
Yes. So we did some prototype design, but never built. And wine tanks, yes, they are. What have been used now is energy dissipation device. There are two types. One is replacing the bolts by unbuckling bolts that it works like a restraint brace, but it's a bolt, and yielding on the bolt, and also putting a flexible connection like an ADAS connection between the foundation and the tank. That's the two options that has been used, not extensively, but it has been used. So buckling restraint bolts with a large energy dissipation capacity, and also the ADAS type dissipator between the bolt and the foundation.
And question 2 from Eren Uçkan. Considering very large amplitude cycles in the 2010 earthquake, did you observe any ultra-low cycle fatigue failure in steel tanks or buried pipes due to wave propagation effects?
Okay, there were a lot of damage in lifelines, but I cannot help you. I don't have the data for that to say yes or no. We have a lot of failures in lifeline. I can, if you send me an email, I'll redirect you to people that are working on that field. I don't feel comfortable answering your question.
And also from Ian Icon. Hi, Ruben. Thank you for a great presentation and your valuable insights. Can you make some more comments about Chilean code vertical stiffness requirement related to 10
Hertz? Yes, this 10 Hertz issue, I think is important. I think we were worried because of some buildings vibrating vertically. Okay, we didn't want that. And the issue, so we are not isolating vertically, okay? So if we are gonna isolate vertically, I'm not gonna use 10 Hertz. That's not the question. So I'm assuming that we don't want vertical isolation, but we saw on the first structure that we isolated, this one, you go to the vertical, actually there was some amplification at the period, vertical period. Actually, the amplification was around 4 times in this building on the vertical direction, not as a total maximum acceleration, but at the frequency content. So we were worried to have, we were measuring vertical, damping on isolated buildings, and the damping was amazingly low. Yeah, we were very worried about that. So we said, what happens if we have a coincidence or resonance and we actually amplify vertically? So at the end of the code, we decided to go 10 Hertz. But then we start having problems because we have small slabs sometimes in residential buildings. And then we get low damping system with coincident frequencies. So then we were more worried, but for the moment has worked. Hope it keeps working because we cannot go lower unless we isolate it vertically, or we put some damping. So in one of the buildings that we were very worried, 20-something story building, we were thinking of adding some friction on the vertical direction in order to reduce vertical vibration. But at the end, it was not necessary. I don't know if that answered your question, Ian. I'm very happy to say hi to you. Hope we can see you soon.
And thank you very much. Another question from Bahadur Shahdan. How do you justify higher damping reduction factors, although most of the earthquakes are near fault? Sorry for lots of questions.
No, it's not near fault. Most of the earthquakes are interface, are intraplate. Mm-hmm. They are not near fault.
And not near fault, okay. From Ümit Özkan from Turkey. When using mixed systems, he means hybrid systems, like LRB and CLB, did you encounter any vertical displacement problems between LRB and CLB, as their vertical stiffness are different than each other?
It was considered and no problem was observed. Okay. These CLBs were practically no deformation on the vertical, as you can imagine. And yes, the rubber will just, if you get the design, can take stress a little bit the isolator, of course, rubber isolator. But at least for the moment, I can tell you no problem. And the CLBs were not included here for vertical motions, but just to have very low friction.
Yes, very low. And also Murat Çelik asks, thank you very much for the presentation. I wonder what range of displacement capacity is needed for the base isolation systems against the MCE event in the high seismic zone in Chile.
We have designed plus minus 70 centimeters.
70 centimeters.
And not controlled by a cortical or surface earthquake. We haven't had that. Actually, we did have a project that wanted us to build on top of an active fault, and we refused the project. So we are not doing everything.
And also, Ümit Özkan, do you have any recommendations for rotations in FPS? Maybe testing with tapered plates in prototype testing.
Yeah, I have no recommendation. I have not enough experience to comment on rotations for that. But the only thing I can tell you that after this damage that I show you here on this system, I mean, this is not, I mean, there is a huge stress concentration on the lentil. And this is something to consider, okay? Of course, some of these systems have releases for rotation, okay? But not all of them. So some of them use rubber to accommodate the rotations, others have a mechanism, so it has to be tested appropriately for the expected rotation.
Okay. And also, again, from Oğuzhan Alperen, again, he asked a question, fourth question. Considering the frequent number of earthquakes in Chile, what can you say about the durability of the isolators? Is there a durability test for one isolators in literature, testing one isolator repeatedly?
There were some cases that you can leave some testing isolators on site that are just easily to remove. They have the same environment and you can test it as much as you want. In our case, I'll tell you, we have one isolated system from the 1980s but it was designed for blasting, still working, not testing, just that it works. The building I show you, 1993, 27 years, not testing, but we know that it works because it's instrumented. So one answer to your question is you should instrument because it's cheap, automatic, and it gives you the answer if you have the doubt. So in our case, we have so many earthquakes that I can guarantee you, and I do it actually, that I will put the sensors, I'll get you data in 6 months. So, we have done it, okay? Not a big earthquake, of course, and we don't control that, but at least some data that will give you some insight before removing the isolator and testing it, okay? So you can always have isolators for testing outside. You can remove your isolators, but that's not too intelligent because of the high seismicity unless you replace it immediately. Or you just instrument and use the test bed that Mother Nature gives you, that is the earthquake. We have also jacket and pull the building with actuators, okay, in case you need it. We have done it also. It's expensive, more expensive than just putting sensors and waiting 6 months in our case.
Okay, İlkin Sevigen asks, what is the maximum horizontal displacement have you ever observed? But you already answered, yeah. I think, 70 centimeters, if I'm right.
Yes.
Also, Alessandro Martelli has some comments. Can I read? I strongly support the use of seismic isolation for protection of high-risk plants, not only nuclear, but also chemical, like LNG tanks. There are some important applications in some countries, including Turkey, but only few in Italy, just 3 small tanks. I am now collaborating with international agency, I think Atomic Energy Agency, because abbreviations we used, for increasing the use of seismic isolation of nuclear plants too. Which is your opinion, Ruben?
Definitely. We have 3 tanks in Chile that are base isolated, 80 meters in diameter. LNG, so not a small one. Actually, when you go inside, it's like a church. It's a huge. One of them on rubber isolators, 2 of them on friction pendulums. One of them was built during the 2010 earthquake, but it was completely surrounded by dirt, so it didn't move a millimeter because it was completely confined because it was a construction stage. And the pity is that no instrumented data is known, but they have been experienced earthquake, and I think it will be not only good to promote the isolation in this type of structure that we have designed many but not built one yet, but to instrument it, because without data we are losing a key component. I think again the paper by Calvi and Calvi shows that we need more information because our models are not so suitable and cannot model everything. Okay, we still have lack of knowledge, and we should have not only isolated structure, but also instrumented structures.
Okay. Bahadur Şadan asks, do you have any testing facilities in Chile?
Yes, but not for the large earthquakes. So for the isolators, we go to Pavia, San Diego. For very large ones, small one, we can do it. A small one, we can do it in Chile. Yeah.
You have the independent third-party laboratory, yes?
Yeah, more or less more or less independent. Let's say not 100% independent, but more or less independent. So what we do is, this is an important issue because laboratories for isolators that are independent, you have Taiwan, Italy, and California, but there are not so many. And sometimes you make a huge queue waiting for testing. So actually the manufacturers have to have a lab in order for to test, and it has to be a qualified lab, and it has to be open for review. And I think that is important. It has to be a standard lab, but with open access until we have enough independent labs. We have to be realistic. We would like to have all of them independent, but we can't. There is no such a market yet. So at least we have the manufacturer, but it has to be an open lab, okay? And they have to supply everything. I'm not so happy with some of the standards in some countries that they don't allow you to have all the test data. For example, in friction pendulums, they don't give you the first cycle of the testing. Yeah, that is not reasonable, okay? Because there is a lot of information in first cycle, and also huge amount of cycles that are done too slow, or we have one case that before testing, they put oil on the surface, sliding surface, and then they test it and then go back and put another oil. So this type of things has to be limited. I mean, we cannot do independent testing with this type of attitude. It's not common, but it does happen. So we have to restrict this thing.
Okay, Bahadur Shahdan asks another question. Are there any applications where high damping rubbers bearings are used? What are your thoughts?
We did start with high damping rubbers. This is a small building, and a few of the bridges, the first bridges we did were with high damping rubber bearings. But the issue of time, aging, and the huge variance of the material properties due to aging show us that it will be better just to switch to lead and natural rubber, but not too much lead. Okay, so also it's not that we will have a huge 20% or 30%, I mean 25 or 30% damping with lead. This is, we will have another type of problem later, okay? So we did high damping rubber bearing, we start with that, but then we switch out because aging problems.
Okay. Alessandro Martelli has comment to you. You are right, Ruben. Monitoring of plants is extremely important. And I think also there are some comments from Şahin Güvercin. Thank you very much for your nice presentation, Mr. Boroschek. Greetings and respect from Turkey. We thank the Turkish Association for Seismic Isolation and those who contributed. Also, Şevket Ateş from Trabzon. Thank you very much for your nice presentation, Dr. Boroschek. Greetings and respect from Trabzon. I think no more question. We have covered all of our questions. Is there anything else you wanted to cover before we finish, Dr. Boroschek?
Well, I want to thank you for the invitation. And I think we should promote together through ASISI and the use of this technology and also energy dissipation devices. I think it's important. It's an option. We should always try to isolate because we don't get the energy inside the structure, but sometimes there is no other chance. And there is plenty of options there, but we still need to instrument. So in order to share the knowledge within ourselves. So I just want to thank you, everybody. Wish you a happy year and hopefully everybody's safe with this COVID situation, but allow us to share more freely through the internet. And that is good. I think that's the only positive thing I can imagine for the moment.
Great. Thank you, everyone. We appreciate you being here. We will continue webinar series. Therefore, please follow our social media accounts for our next webinars. Thanks again for joining us today, and we will see you next time. Thank you, Dr. Boroschek.
Congratulations.
Okay. Thank you very much.